So dear students, having completed the fundamental ideas in the ensemble formalism, we are now in a state to discuss the canonical ensemble and the grand canonical ensemble as a separate module as per the syllabus. So here I have given the third module of our syllabus, whose central theme is further discussion of ensemble formalism, and in this module we will be focusing on the remaining two ensembles, the canonical as well as the grand canonical ensemble. In the elements of ensemble theory module, the previous one what we have just completed, we have introduced the concept of ensembles as a powerful technique to understand the thermodynamics of a system statistically, and in this particular module we will be making further modifications in the ensemble formalism, and we'll see how practical systems other than the ideal systems can also be analyzed by using the same formalism. So the method of micro-canonical ensemble that we have familiarized ourselves in the previous module is applicable only to systems which are isolated, and we know that truly isolated systems are only an idealized concept. We do not have perfectly isolated systems in nature. Okay, or we can say that keeping the total energy of a system constant is physically inconvenient or impractical. Hence, in most of the systems of our physical interest, we focus on the temperature of a system as a convenient parameter in place of the total energy of the system. Okay, and syllabus points can be seen here. So just have a glance at the syllabus points. So the module will be having both the discussion of canonical followed by the grand canonical ensemble, and the topics discussed under the two ensemble formalisms will be more or less the same. Okay, only the difference will be in the methodology, and we'll be seeing each of this one. So the reference for these two or this particular module will be still Patria chapters 3 and 4, the statistical mechanics by Patria, the textbook, and you can use any other equivalent textbook like Huang or any other thing to get the related concepts. Okay, so let me just go to the particular module. We will start with the canonical ensemble first, and then we will extend our ideas to the grand canonical as well. Okay, ensemble as well. So as I told you, the micro-canonical ensemble that we have been using so far, the micro-canonical ensemble, we introduced the simplest kind of ensemble, okay, to begin with. So the micro-canonical ensemble was introduced as an ensemble, or it was introduced as a collection of a system with its large number of mental copies, each sharing the same macro state NVE. NVE was the macro state of the system in ensemble, or all elements of the ensemble was sharing the common macro state NVE, but in all different possible micro states. So that collection we named as what micro-canonical ensemble. And we have seen that the number of particles in the system is constant. Okay, the volume, of course, the volume of the container or the volume of the system is also what constant if you consider a gaseous system. And the condition was that the total energy of the system must also remain constant. And when the number of particles and the total energy of the system must remain constant, it means that we call such systems as what? Isolated systems. So that is what we have just started with. Okay, so the micro-canonical ensemble formalism that we have introduced is only an idealized concept. It's a pure idealization, because it represents, or it is suitable only to analyze theoretically isolated systems where the number of particles and energy is remaining fixed. And I hope you remember that towards the end of our discussions of the micro-canonical ensemble, two examples were discussed. Okay, one was the classical harmonic oscillator, and the other one was the ideal gas. So in both of those discussions, we had made some relaxations to the condition that the energy of the system should be remaining constant. I hope you remember we permitted that the energy can have a small spread delta, where delta is very small. Okay, and we did it only to make it at least come closer to the reality. Okay, because having isolated systems is actually beyond physical reality. So my conclusion is that the micro-canonical ensemble formalism that we have already introduced, okay, was the simplest type of or idealized type of ensemble formalism, and that was suitable only for the theoretical treatment. Okay, and therefore for practical systems of our physical interest, for practical systems we will be preferring either the canonical ensemble or the grand canonical ensemble, because we have seen that a canonical ensemble is representing not an isolated system, instead it is representing what is known as a closed system. Okay, closed thermodynamical system, closed system. And a grand canonical ensemble is actually representing what is known as an open system. So in nature, in physical reality, we are having either a closed system. Of course, a closed system is possible because you can close the container such that the total number of particles in the system can remain constant, permitting the exchange of energy. The boundary can be a conducting boundary, still the system is closed. Okay, and grand canonical ensemble is, of course, that is the most common type of systems that we come across, where the number of particles may change and also the energy can get exchanged, right? So that is what I have to mention as a thing. The most practical form of the most effective ensemble formalism to analyze a real system will be the canonical ensemble. Okay, and we will of course talk about the grand canonical ensemble later. So what is a canonical ensemble? Just go back to our definition of ensembles. Every ensemble will be characterized by a system along with its large number of mental copies. And how do all these ensembles, one ensemble is different from the other one? They are different from the other one in the macro state. In the macro state description, you can see that in the canonical ensemble, which represents a closed system, the system is characterized by, or every member of the ensemble or every element of the ensemble is characterized by a macro state, NVT. The macro state is NVT. Just always make, I once again seek your attention. The macro state for any system in micro-canonical ensemble was NVE. The energy was remaining constant. But you can see that in the case of a canonical ensemble, instead of or in place of the energy, what assumes relevance? The temperature is now remaining constant. So in canonical ensemble formalism, all systems, or a system along with all mental copies, or we can say all elements of the ensemble is supposed to be sharing same temperature. They are all sharing the same temperature. We just demand that they have same number of particles, they are all having the same volume, and they all have a constant temperature, or they share the same common temperature. Which means that we relax that the energy is a constant. Energy need not be a constant. The systems can exchange energy with the surroundings. So energy can get exchanged until, but the condition is that finally the system should be achieving a state of thermal equilibrium. Where the temperature of the systems, all systems should be remaining achieving finally a constant. So that is the idea. So the most important idea is that a system in canonical ensemble shares the same macro state, common macro state, NVT. NVT is the macro state. So here the first sentence in the slide is just giving you a definition of what actually is a canonical ensemble, and this definition you have already just seen. So a system characterized by the macro state NVT, where the symbols have their own meaning, along with its large number of mental copies. We call all these systems as elements of the ensemble, which are in thermal contact with each other. So what is meant with thermal contact with each other? So hope you remember we had a schematic diagram of canonical, micro-canonical and grand canonical ensemble, where we represented the canonical ensemble like an array of systems like NVT, 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 Okay, so the boundary of the systems, each of the system has got a boundary, and this boundary was I told you the boundary is a conducting boundary. Okay, whereas in the case of a canonical micro-canonical ensemble, we told that the boundary is adiabatic boundary, and in the case of grand canonical ensemble, hope you remember that we made that the particles also can just get exchanged, so the boundary is a say permeable boundary or a porous boundary. Okay, hope you remember that thing. So in that sense, since the temperature is remaining constant for all elements of the ensemble, we can say that schematically the members of the ensemble will be in thermal contact with each other, so that energy can be exchanged, okay, either between themselves or with the system along with the surroundings. Okay, so that's about thing. Now I told you that why do we, okay, this is what exactly what you have to understand. Why do we go for a canonical ensemble as a practical ensemble formalism compared to a micro-canonical ensemble, which is theoretically ideal? The reason is that okay, we have seen that energy is the parameter in micro-canonical ensemble. Keeping energy fixed for a system is pretty difficult. Okay, or making a system perfectly isolated physically, actually physically it is impossible. Okay, we do not have physically the total energy remaining perfectly constant. But we know that in thermodynamics, the temperature, it's a parameter which can be easily controlled. Okay, so in place of energy, or compared to the energy of a system, the temperature of the system is a quantity which can be easily controlled. You know that, okay, you can increase or decrease the temperature of any system, okay, by heating or by cooling, okay, or letting it to cool by itself. You can just control the temperature of a system easily. Okay, but a direct control on the internal energy of the system is often very difficult. And not only that, okay, controlling the energy is okay, rather than controlling the energy, measuring the internal energy of a system is often okay, a very difficult okay, actually process. But you know that unlike the energy, total energy or the internal energy of a system, you can directly measure the quantity what is known as what temperature. Okay, so why we go after, so I'm trying to answer one very important question that should be kept in your mind. Why do we prefer a canonical ensemble in place of a micro-canonical ensemble? So this is the thing that I'm trying to answer. Okay, you know that a micro-canonical ensemble, I'm summarizing, it is characterized by NVE. This is the macro state, means energy should be kept a constant. So in order to see that some quantity is kept a constant, you should be able to measure it accurately, first thing. And second one, you have to maintain that quantity as a constant, means you have to control it. So there are two things, that the quantity should be measured, and the other one is that the only if you are able to measure the quantity accurately, you will be able to control the quantity. Okay, and measuring internal energy of a system, we don't have direct methods to measure the internal energy of the system. We don't have internal energy meters. Okay, instead, you know that in place of energy in the canonical ensemble, the systems are characterized by N, V and T. So you can see a clear replacement of energy with what temperature as a parameter. And what is the advantage of temperature in the entire thermodynamics? You know that, okay, temperature is one of such physical quantities which can be easily measured by using devices like thermometers. There are pretty different types of thermometers, so you can use any suitable range of thermometers to measure the temperature of a system. And once you are able to measure any physical quantity, okay, means you are able to, you have a method to control it. You can either increase that quantity or decrease that quantity by allowing heat to flow in, or removing heat from that. So due to this very reason itself, we prefer a canonical ensemble as a practical ensemble formalism in place of what a micro-canonical ensemble formalism. But remember, of course, the micro-canonical ensemble formalism is very easy to theoretically construct it. Okay, the reason is that micro-canonical ensemble formalism is suitable for treating the perfectly isolated system, which is an idealized concept. Okay, so isolated system means we do not bother about what, no exchange of particle, no exchange of energy. So it is very easy to analyze theoretically to develop the theoretical formalism, micro-canonical ensemble is rather easy. Okay, but once you are familiar with the ensemble formalism, now we are in a state to take the discussion to practical systems using what? Canonical ensembles. So to conclude, let me say that a canonical ensemble can be regarded as a closed collection of isothermal systems. Okay, a canonical ensemble, as I told you here, see that this is the picture that you have to recall. See, a canonical ensemble can be, ensemble is a collection of system with along with the large mental copies. So what is a canonical ensemble? You can just regard that a canonical ensemble is just like this. So this is a system of n particles having a volume V and a temperature T, say. Now, to make it as an ensemble, we consider what? Another such system, okay, having the same macro state NVT, sharing the same macro state, but the second system will be in a different micro state. Okay, means and you can take maybe a third one where the third one is also having the same macro state, okay, but in a different micro state. So likewise, you take all collection of all large number of all these, okay, see that all these should be having same volume and all. So you just consider an array of such systems. So this is just to make a mental picture. Okay, and since we have seen that the temperature is a constant, we don't insist, we don't demand that energy should be a constant. So which means that you can assume these members of the ensemble can just permit what? The exchange of energy between the thing, but no exchange of what? Particles. So that is why we have just given this statement: canonical ensemble, CE stands for canonical ensemble. It can be regarded as a closed collection. Closed collection means this entire thing is what? Okay, just enclosed, means okay, the total number should be remaining constant. Okay, and there is no permission of particles to get exchanged between system and the other element of the system. Okay, so regarded as a closed collection of isothermal systems. Isothermal system because each of them are having the same temperature. So a large number of isothermal systems are kept in what? Thermal contact with each other. Okay, such a collection is very similar to what is known as an ensemble. So what is practically done is that in thermodynamics, to study the thermodynamics using canonical ensemble formalism, what we do is that we will be taking the system. Okay, so let me say that this is the system. One of this original system I am representing here. Okay, so this is having NVT, and all other members of the ensemble, all other members of the element or all other elements of the ensemble is regarded as what is known as a reservoir. Okay, so this is another method. We will consider the system and the other elements of the, for example, suppose that in this picture I'm considering this one as one of the member of the ensemble as a system, and all other things, the rest of the system is regarded as what is known as what? The surrounding. So it's just like in the thermodynamics we have the system and the surrounding. So all the rest of the elements of the ensemble will be serving as a surrounding in the in one of the ensemble method. So remember what is the fundamental aim? What we are actually trying to do using ensemble formalism is that a system, a physical system. Okay, a physical system. For example, it can be a gaseous system, it can be a laser system. Okay, so you consider any system. So I'm considering a gaseous system, for example. A system can have a large number of energy levels, that. Okay, physically speaking, in the energy spectrum, okay, a system can have a large number of energy levels. So say that it can have E1, E2, E3, E4. Likewise, I'm just naming it as this is E1. Second one is E2, third one is E3. So these are all E4, E5, etc. So these are all different energy levels. Okay, having a wide variety of distribution of the gap between the energy levels all will be different. Okay. For example, hydrogen atom, that it has got a ground state energy of minus 13.6 electron volt, followed by the n equal to 2 state, having energy is equal to minus 3 point, value, and then minus 1 point value. Likewise, it goes on, right? So here also you can see that consider any system having a large number of possible energy levels, and these energy levels may be degenerate also. Remember, the concept of degeneracy. What is mean degeneracy? Okay, so same energy level can have different states. For example, if we say that a state is having degeneracy, G is equal to degeneracy usually represented by the factor G. Okay, so G is equal to 2. It means that see, the system will have the same level will be having two different states. Okay, for example, spin up and spin down state. We say that in a level there can be two electrons. One is spin up electron and other one is what, spin down electron. So we'll say that due to that spin there is a degeneracy. It is having degeneracy of 2, means same energy but two different states, right? So likewise, so each of these levels will be having its own degeneracy. Maybe for example, the ground state is having the degeneracy 2. Okay, the second state is also having degeneracy 2, likewise like that, and some other states are having degeneracy 3 or any other number. So it means that suppose that you have n electrons, you say n particles in general, n electrons, you say that electrons are our particles. Okay, don't see, just forget about what is known as the property of spin and all. We'll just start with what, simply some particles whose quantum mechanical nature can be neglected for the time being. Just consider that we have some particles, and these particles has to be arranged in all these energy levels. Okay, these particles has to be arranged in all these energy states rather than levels. Let me use the word states. Okay, now you know that there are a large number of ways in which these particles can be arranged in these possible levels, so that the total energy of the system is what, E. You know that the total energy, the system will be having a total energy, in the case of a micro-canonical ensemble. But for the canonical ensemble, you know of course that the system's energy can vary between 0 to E. But let me say that at any instant, let the system be having an energy E, and how the particles of the system will be distributed in different energy levels. How the particles of the system will be distributed in different accessible energy states, which we call as eigenstates, or in statistical mechanics we call it as what is known as microstates, accessible microstates, such that the total energy of the system becomes E. Okay, so means since there is a large number of particles in the system, okay, we cannot exactly make a prediction that at a particular instant this particle will be in this particular energy level. We cannot make a clear prediction of that. Instead, we can only have probabilistic predictions, right? So what we are interested is that, suppose that I'm considering a particular energy level having energy equal to say E2. Okay, so I'm considering the second energy level here in the picture, right? So I'm considering an energy level E2. What I have to do is that I have to find the probability that, the level with E2 is occupied. What is the probability for the system to have the level with energy E2 is occupied? Or we can say that we have to find out the probability at any given time that a state with the energy E is what, occupied. Or instead of E2, E3, E1, etc., let me use a common symbol ER. Remember, this R is used for just like En. Okay, ER. Okay, so this is the symbol that is used. R is taken as a dummy variable in place of E1, E2, E3. I'm using E1, E2, E3, etc. We are using, usually we have been using En. Instead of En, Petria prefers to use it as what, ER. That's all. So let me say that the fundamental aim, you can see that the fundamental aim in ensemble formalism is to find out the probability PR. It's not P into R, just take it like P. P stands for probability and this R is a subscript. So take here also this R is a subscript. Okay, so we have to find out the probability PR represented by PR that, so what is this probability standing for? That at any time t, at any given time t, we let the time to pass on. Okay, a system means the system that we are trying to study, the system whose thermodynamical properties we are trying to analyze. A system in the ensemble, a system in the ensemble means it will be in any one of the accessible microstates, because each element of the ensemble represents what? An accessible microstate of the system. right? So a system in the ensemble means a particular member of the ensemble is found to be in one of the states with energy ER. Okay, here also this ER you have to take. So this R is a subscript, it's not E into R. So what is we are trying to do in every ensemble formalism is that a system is supposed to be having large number of energy states, say E1, E2, E3, E4, etc. up to En or ER, and ER is one of that energy state. What we have to do, or what is our aim to do, is that we have to calculate the probability that at a given time t, the system is found to be in a state with what? Energy ER. What is PR? So PR is the probability that the system is found. Okay, or see, we can say that the probability that a particular energy level ER is occupied. We can say like that. For example, there is a 3 level, or say that, for example, you are studying about a laser systems and all. Consider that this is E0, energy is E0, we call it as ground state. Okay, and this is having energy E1. And this is having energy E2. Suppose that this is a 3-level system, one of the active medium in the 3-level laser system. Suppose that E0, E1 and E2 be the energy levels corresponding to R is equal to 0, R equal to 1. Instead of N, we are using the symbol R, that's all. R is equal to 2. Now suppose that there are 100 particles. So this is the total number of particles in the system. NVT, N is 100. Of course, N will be of the order of Avogadro number. I'm taking some practically easy to handle numbers. Okay, suppose that there are 100 particles. Now, suppose that system is at thermal equilibrium. The system is at thermal equilibrium at a temperature T, say 300 Kelvin. System is maintained at 300 Kelvin, means what? The temperature is remaining constant, number of particles is fixed. Okay, and suppose that the energy of the system can vary. So the question is that if the system is achieving thermal equilibrium, how these 100 particles will be getting distributed among the 3 accessible energy levels or 3 accessible energy states. I'm not considering degeneracy at all. Okay, I'm just taking that each energy level is having only single state. Okay, so how these 100 energy levels will be getting occupied? That's a very important question as far as laser systems are concerned. I'm talking about laser system because that is a very quite familiar system that you have learned. Hope you remember. So what is your prediction? At any particular temperature, at a low enough temperature, say 300 Kelvin, very close to room temperature, out of these 100 particles, okay, what would be the distribution of these 100 particles among the 3 given energy levels? What do you say? What do you feel? Of course, I think you remember that usually in a state of thermal equilibrium, most of the particles of a system will be found in the ground state. You know that. Most of the particles will be found in the ground state, and that is what we usually discuss while we discuss about what the ground state population. The ground state of any system is heavily populated. That is usually at any temperature, the ground state is usually heavily populated. Okay, and hope you remember that when we studied laser systems, the principle of laser systems, discussed about a very important phenomenon, what is known as the population inversion, right? That for the laser system to work, you should first obtain a condition what is known as population inversion. What is that population inversion? Because usually the ground state is highly populated. Okay, but for continuous laser emission, that there should be a large number of particles in the excited levels or upper energy levels, say E1 and E2. Then only with some trigger, you can have say continuous laser emission, stimulated emission, right? So that if I just draw the population of the different levels like this, you can see that mostly the ground state, lower energy states will be having higher number of occupancy. The higher and higher energy levels will be having lesser and lesser occupancy. That is usually the way in which particles will get distributed in order that the system is having a stable equilibrium. Because the system has to be, every system will try to maintain lowest possible energy configuration, okay, at a given temperature, right? So that it is attaining maximum equilibrium, right? So for that, so you can see that in this particular example, what I am talking about, you can see that out of 100 particles, you say that some 70 particles are in the ground state, some 20 particles are in the second or first state, and remaining say 10 particles only are in the third state. So what we are discussing is that what is the probability of occupancy? What is the probability of occupancy of the zeroth state or ground state? Okay, what is P0 meaning? P0 means the probability that, okay, the probability that the state with energy E0 is occupied. Now we are interested in finding the probability of the first state. Okay, what is P1? P1 means it is the probability that the state with the energy E1 is occupied. It's the probability that the state with energy E1 is occupied. And the third one is that I have taken an example of the 3 level systems. So P3, what is P3 meaning? So let me call it as P2 for example, okay, because 0, 1, 2. So P2, what is P2 meaning? P2 means it's the probability that the state with the energy E2 is what occupied. Okay, right. So you can see that we expect, since these 100 particles should be somewhere either in ground state or E1 or E2, we can say what do you think about P0 plus P1 plus P2? Okay, what will be the answer of P0 plus P1 plus P2? Of course, you know that this thing should be equal to 1. Why should be equal to 1? Why should be equal to 1? Because you know that the total probability should be equal to 1, because this is statistical probability, not the thermodynamical probability. Remember, we have been using a symbol omega or gamma for thermodynamic probability, which I told you is not statistical probability. That is the number of microstates. But here what I am talking about, this P1, P2, P3, or in general as PR. PR is nothing but the pure statistical probability, okay, whose total value is equal to 1, right? So what we are doing, that's where I would like to just focus on this one. The fundamental, once again I'm back to this particular sentence, I am trying to explain this sentence. The fundamental aim in ensemble formalism is to find out the probability, which we are representing as PR, that at any time t, a system in the ensemble is found to be in one of the states, okay. A large number of states are accessible, and what is the probability that a system is found to be in one of the states with an energy what? ER, with an energy ER. So that is why the symbol R is there. So P1 denotes the probability that the system is found in a state with energy E1. P2 denotes the probability that the system is found in a state with E2. P3 denotes the probability that the system is found in a state with what? E3, and so on. So our fundamental aim is just to calculate PR, just to calculate what? The quantity what is known as probability that a system is found in a state with energy ER. And that is what we are going to do in the ensemble formalism throughout. Okay, so before I end up with this particular discussion, okay, before we go to the real thing, let me just give you an overview of what we are going to do next. Okay, and thereafter we will just continue. So remember, so as I told you, the fundamental aim is to find out a relation between the probability PR and the energy ER of the system which can be accessed. Okay, now there are two ways, there are two different approaches that is used to find out the relation between energy ER of a system and the corresponding probability PR that that particular level or state is occupied. There are two approaches to find the relation between PR and ER of a system. Okay, the first approach, in the first approach we will be discussing both the approaches in detail in the coming sessions. The first approach, just you listen, okay, for the time being. The first of the approach is to regard our system to be in equilibrium with a heat reservoir. We will be regarding our system, okay, suppose that this is our system having macro state NBT. We regard this system to be in equilibrium. Which equilibrium? Thermal equilibrium with a heat reservoir. Let me say that this is my reservoir and this is a system. You know, reservoir means everything, okay, just other than the surrounding, what we call as reservoir. Yeah. So this is a system and this is the reservoir or the surrounding at a common temperature T. So both the reservoir and the system is sharing the same temperature. You know that, what does it mean? It means that this boundary is a conducting boundary, right? Okay, the boundary is supposed to be a conducting boundary because you know that the temperature should remain constant in canonical ensemble. Okay, in order to maintain the temperature as a constant, you should permit the energy to get exchanged, so that energy exchange can happen over the boundary. So the boundary here is a conducting boundary. That's why we say that this micro-canonical ensemble, sorry, the canonical ensemble, the systems are what having a closed, they are representing closed systems with a conductive boundary. No, particle exchange is not permitted, but energy exchange is what permitted, right? So the system is considered to be in equilibrium with a heat reservoir at a common temperature T, and with this assumption, what we will do, we will study, I have underlined something, we will study the statistics, the probability, the chances. Studying the statistics means we are studying the probabilities or the chances, okay, probabilities or chances, okay, using mathematical methods that we will see in the next sessions. We will study the statistics of the energy exchange that happens between the system and the surrounding. So our focus will be on studying the way in which energy will be exchanged between the system and the surrounding, so that finally both of them will be attaining a common temperature T. So that is one method. Okay, and there is yet another method. Okay, we will be discussing these methods in detail in the coming sessions. Don't worry about any of this. I will be referring back to this particular method. In the second approach or second method of canonical ensemble formalism, we will be regarding, this is the true ensemble method, we will be regarding the system as a member of the canonical ensemble. Okay, in the earlier approach, we were not regarding, we were not considering the concept of ensemble at all. That is actually a purely thermodynamical method. But the second approach, which is a purely ensemble formalism approach, we will be regarding the system as a member of the canonical ensemble or NVT ensemble, in which an energy E, see, I am using a different symbol for energy now. An energy E is being shared by N. I am trying to use the script letter N. This N I am trying to use. Okay, so this is the same N that is used by the symbols used by Patria. Okay, so the total energy E is shared by N identical systems of the ensemble. The total energy E is being shared by N identical systems of the ensemble. Okay, right? So it means that suppose that I have just a total energy of say 1000 joules. 1000 joules is the total energy. Okay, and suppose my ensemble is having say 10. I'm just taking very what you can say that which is practically not the thing. I'm taking very simplified toy models where I can handle with the numbers easily. So we say that let there be 10 systems in an ensemble. You know that the systems in an ensemble will be very huge, okay, larger than the Avogadro number practically, because each microstate should have one member, okay, and the number of microstates is going to be pretty large. Okay, so let me say that totally there are some 1000 joules of energy. Remember, so that total energy of all systems, all members of the ensemble is what I am representing as E. And how many systems are there in the ensemble? Okay, let's say that there is only 10 systems. Okay, this 10 system means what? They are representing 10 different accessible microstates. So in my example, there are only 10 accessible microstates. So each microstate is represented by one element. Okay, so there are 10 such mental copy systems, right? Now, what the second method is going to do, we will be discussing or we will be studying how this energy, total energy of 1000 joules will be shared by the 10 members of the ensemble. Remember, this particular 1000 joule can be shared amongst the members of the ensemble in different ways. How? See, it can so happen that one system is taking the entire energy 1000 joules. One system is taking the energy 1000 joules. It means that other elements are getting 0. That is one possibility. And you know that there are several other possibilities as well. Okay, So what can happen is that each of these possibilities denoting what? One microstate actually, right? So what is happening is that by the way in which, or while we complete this analysis, that is which analysis? How the total energy E is being shared by n identical systems of the ensemble. We will be studying the statistics of this sharing process. Okay, and we will be doing a method, what is known as the method of most probable values, method of most probable distribution. We are going to do a method known as the method of most probable distribution or most probable values. Okay, and this method also will be discussing in detail. Both the approaches will be discussed in detail. So these two are two different approaches. See that you read this particular two approaches, okay, and try to understand what is the difference between the two approaches before we go on to the next session where we will be discussing the two approaches in detail. Okay, now what I told is that we can have several methods to study to find out the relation between PR and ER, which is our ultimate aim. Okay, now we have a good news, or we have a good result. What is the good news? The good news is that in what is known as the thermodynamic limit, hope you haven't forgotten. Okay, what is meant by thermodynamic limit? Thermodynamic limit means that the limit where the number of particles of the system is tending to infinity, right? And the volume also is what? Tending to infinity, with the ratio of n to v remaining practically constant. So practically it means that when the number of particles is huge, means for thermodynamic systems or statistical systems. So in the thermodynamic limit, whether you follow the first approach or you follow the second approach to obtain a relation between PR and ER, both the approaches will be giving you the same relation, and that is the good news about it. Okay, so in the thermodynamic limit, which actually our systems are following, the approach number 1, which is purely thermodynamical nature, and an equivalent approach number 2, which is purely ensemble formalism based, both the approaches will be giving you the same output, means you will be getting the same relation between PR and ER. And why we are so particular about getting the probability PR, that the system is in a state with ER at a given time, because this is the conclusion thing. Once the probability PR is obtained, we will see that. Okay, once the probability PR is obtained for a given system, the entire thermodynamics of the system under focus can be evaluated, and that is actually the heart of the thing. Okay, so maybe you are wondering now because you haven't seen the entire picture now. Okay, so remember that why do we focus on calculating the probability that a system is found in a given state with energy ER? Because once you are able to calculate the probability PR for a given system, then the entire thermodynamics of the system that you are trying to study can be evaluated just from the knowledge of this PR. Okay, it's very similar to what what we have discussed in the micro-canonical ensemble as well. In the micro-canonical ensemble, hope you remember the basic recipe of the ensemble formalism. Okay, you know that in micro-canonical ensemble, our focus was to calculate the quantity sigma or omega or this particular thing, right? So any of this thing, what is that? Which is nothing but the number of accessible microstates. Our entire aim was to calculate the number of accessible microstates represented by any of these symbols, and using the symbol, then we went for calculating. Okay, what is that? S equal to K log omega, okay, is it not? Or W, whatever it is. And from S, using thermodynamics equations, the partial derivatives, we calculate every other pressure, the temperature, the chemical potential, every other thing we have calculated. So that is the recipe. So you know that our ultimate aim in micro-canonical ensemble was to calculate omega of the system, which is the thermodynamic probability of the system. In place of the thermodynamic probability omega, our fundamental focus in canonical ensemble is to calculate a very similar quantity, which is what? PR. So once we are able to calculate the PR for a given system in canonical ensemble, by following either of the two approaches that I have discussed, you will be able to get an opening or a window into the entire thermodynamics of the system that you are trying to understand. Okay, so in the next session, that was an introduction. I want you to read the relevant portion of the textbook, okay, until you understand what you are going to try to discuss, okay, or you can just read any other relevant notes. We have shared a large number of very useful notes with you in your Google Classroom. So either Jahir Sar's notes or MCT's notes, you can just use any notes. You can use any other relevant material until you understand what we are going to do. Okay, so that we can just have a smooth transition to the method of canonical ensemble with the further discussion. Okay, I know, of course, it was a much lengthy introduction to canonical ensemble formalism, but certainly, just you can take breaks in between and watch it repeatedly until you understand what I was trying to tell you. Okay, thank you.